Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Good morning, Mike.
Hey there, Happy New Year.
Happy New Year to you, 2026. Did you resolve anything in relation to the show? I'm springing this question on you without any forewarning. And just to be fair, I will tell you I have no resolutions whatsoever with regard to our show. Just to keep going.
I have no specific resolutions, although I do think and hope that we will hit episode 100 sometime in 2026, which will be a fun milestone.
We could do that. We only need like 10 episodes or something.
I think we need 10 or 12 more, 11 more, I guess, beyond this one. So we should make it. And when we started this podcast, we kind of talked about like 100 episodes was like a key milestone, because if you've made 100 episodes, then you can officially say that you have made a podcast.
So we'll be in the guild then. We'll be card-carrying members of the podcast guild.
Yeah, I'm pretty sure that you get a tattoo or something like that when you hit 100 episodes.
And a health plan.
Right.
Tattoo's a good idea. We could do bro tats.
My only personal resolution for 2026 is better browser tab management.
Okay, now, my friend, I've known you for more than 10 years at this point, and I would bet that 8 out of those more than 10 years, your resolution has been better browser tab management.
Yeah, but this is the year. I can feel it.
The year the Linux desktop and the year Mike's browser tab management finally achieves what he wants. Mike, I've been listening to an Aesop Rock record. It's called I Heard It's a Mess There Too. And I'm just kind of like helplessly, foolishly in thrall of the fandom of Aesop Rock. Every time he releases something, it's like I have to hear it. And I get the sense that he writes his music like almost obsessively. Like, I don't think he can stop writing this stuff even if he wants to. I think he's actually talking about that. But I really like this record. He seems to put one out every year. I like this one a lot. There's a lot of really good stuff on it, and it goes like song to song to song, and they're bangers. He has this one on here called The Cut I really like, and then the one after that is called Full House Pinball. As he starts talking about heaven in the song, and he's sort of like saying, "Yeah, that sounds lame." It's like it's not really as cool as just sitting in my house on a chair with my cat on my lap. And then he says, I heard it's a mess out here. Or no, he said, it's a mess out here. I heard it's a mess there too. And I kind of like that. Like, whatever. Everywhere sucks. He's just rejecting all the many possible heavens that people imagine. And it's just like his goals are like not ambitious. I like it. It's still funny. It's still this like crazy bonkers poetry. And I remain in awe of the work. But at the same time, it's like I relate to the speakers so much. And probably foolishly so. I'm probably nothing like this person. He's so funny and so brilliant. I cannot, but I have to hear it every time he comes out with something new.
I read recently that he is a graduate of Boston University. So shout out to BU, where my son teaches.
Oh, interesting. An alumnus of BU. Got it. What do you got? Did you hear this record? Did you listen to it?
I'm not sure that I have. I'll have to go check it out. I am a fan. I just don't seem to encounter them as soon as you do.
Yeah, he stacks them up. So you kind of have to, it's like, oh, I missed the last 4. Let me go and, unless you're like waiting for them to drop, I guess, which is what I did with this one. What have you got? What have you been listening to? End of year, beginning of year stuff?
So the thing that I've been listening to kind of nonstop during the holiday season is actually from 2023. It's an album of classical guitar by a guy named Raphael Felich. And I apologize to French speakers for mispronouncing that. But he made he's a classical guitarist, which I am a big fan of classical guitar. And in 2023, he made this album called Visage Baroque, which is mostly Bach, but also some other Baroque composers. There's kind of a long tradition of people playing Bach pieces on classical guitar because pieces for piano and violin tend to transcribe well for classical guitar. And so,
Oh, I didn't know that. I have a really, really dumb association with classical guitar. I think that there were moments in previous years, this time of year, where I'm with like my grandfather doing Christmas shopping, and you walk into these like homey wood panel places, and they're always playing classical guitar. So I hear classical guitar, you talk classical guitar, I think, okay, Christmas shopping and classical guitar. That's my connection right there, and it feels really dumb, really dumb connection.
there may be a little bit of that vibe and why I've been listening to this. I know that classical guitar does kind of sometimes inspire like Windham Hill, new agey elevator music type stuff also.
Sweet
but
crystals and yoga and stuff.
This is not that.
Okay.
And no offense if that's your thing. I don't know why, but I really like this. I mean, I listen to numerous classical guitarists and they're all kind of amazing, but there's just something about this guy that is different, qualitatively different in his playing. I suppose some of it may be the recording as well. I just keep listening to it, and I'm really kind of amazed by his talent. You know, it's hard to do a piece that 1,000 other people have done and that's 400 years old and give something new to it. But I find his renditions of these pieces to be pretty unique and pretty inspiring. So if you're into that sort of thing, you should check it out. I might put it in the show notes because it's hard to search him because his name has a difficult spelling. But yeah, check it out. Also, when this show comes out, we will put in the show notes a Spotify playlist with various tracks from things that we've talked about on the show during 2025. So just like we did last year, we will put out a Picture Me Coding playlist for the year.
I'm already picturing it, Mike. It's got Aesop Rock, Viagra Boys, and classical Baroque guitar. It all just flows just cleanly, one track to another.
A little bit of death metal, a little bit of black metal, but not the Nazi sort of black metal. So,
okay. So we're going to have a playlist for 2025 if you would like to torture your ears with the bizarre connections from black metal to Baroque guitar to actually that's not really a weird connection. And friends, if you'd like to support our show, support us as we shoot for the stars, try to make it to 100 episodes. Consider supporting us on Patreon. We have a $4 a month membership level, and we will use your donations to fund the production of the show, including editing and mixing and drinking coffee. $4 a month, about enough to give us 1 cup of coffee a month. So very helpful. Thank you so much to our existing subscribers. We genuinely appreciate your support. And again, if you'd like to reach us, you could send us an email, podcast@picturemecoding.com, or you could see us on Blue Sky, where we sometimes hang out under Picture Me Coding. Now, Mike, this week you had a topic you wanted to cover. And as soon as you said the topic, I was like, yes, I want to know about this thing. Can you introduce it for us?
Yeah, so this is our first episode of 2026, and it's our first episode of season 4, which we arbitrarily decided to start at the beginning of the year.
Oh, I didn't even put on my new season clothes. I didn't know we were starting a new season.
Yeah, I was a little disappointed that you didn't have your new season lucky shirt on.
I'm wearing the wrong socks.
Anyway, we thought we had to go for something big.
Oh,
so
okay. Okay, I didn't know that either. You just gave me this topic. I was like, that sounds cool. It's a big one. Got it.
We decided to go for the biggest cloud service there is, we think, probably.
Oh.
We don't really have data on that. Mm-hmm. But anyway, we're going to talk about Amazon's S3, or Simple Storage Service. And I guess generally about the concept of cloud object storage and how it's kind of a new thing and has inspired some new ways of doing things.
It's mind-boggling how ubiquitous cloud object storage is. It's like if you are a member of this planet and you have used a website, then you have probably benefited from cloud object storage, which is probably used by that website or whatever service provider the website's built on top of. It's insane. It's insane how widely used this is. And you know what? Also, Mike, they have the word simple in there. When I first started learning about it, I was like, "Oh, that's simple." And then the farther I went, the farther I was willing to leave behind the word simple. Where are you on the spectrum of Amazon S3 simple storage service? Would you keep the simple or would you swap it out for something else?
I would say that it's simple to use, sort of. It's not at all simple in its implementation.
Okay, all right. Simple to use is what they're going for there.
Yeah, I'm not quite sure compared to what. I suppose that compared to like firing up a relational database or something and trying to store data in that, it's a little bit simpler.
Mm-hmm.
And we'll talk a little bit about how it's implemented in its API. But
or like launching a bunch of virtual machines in the cloud that all have disks and trying to put your files on a bunch of disks distributed across all of these virtual machines. That sounds complicated. So maybe simple in this case is just an adjective for using it, kind of like a tasty sandwich. Simple plays the same role as tasty in a tasty sandwich.
Also, it allowed them to call it S3. So
which
had they not used simple, they would have had to you call it S2 or...
Yeah, I guess that. And they already had EC2. Oh, no, they didn't have it. Simple storage came first, right? 2006. So the little bit about this service. S3 was launched March 14th, 2006. That was earlier than I would have guessed 2008. It is a storage service, right? So you can send files into it, data, arbitrary binary data, whatever you want. And it's got this HTTP API in front of us. So you just send in these like HTTP requests. I want you to store this file. I want to get the file back. I want to delete this file. It's made up of hundreds of microservices. I was surprised to read. Were you surprised by that?
I had seen a post a long time ago by Werner Vogel about
CTO
S3
of Amazon, yeah.
Yeah, and he had also said something about the hundreds of microservices involved in S3. And I, at the time, remember thinking, that sounds wrong somehow. It just doesn't seem like that's a good idea. But they obviously make it work. And they talk a bit about how, it's not just hundreds of microservices. It's actually like different groups within Amazon that are effectively independent. And, they just are communicating via API contracts.
Yeah, it's crazy sounding. Yeah, and maybe each microservice of the 100 microservices is each one is a 2-pizza team potentially.
That would be my guess. I mean, that's their thing. Yeah, the idea of something which is composed of hundreds of microservices is really hard for me to fathom. Mm-hmm. That it's working together as, you got to assume that some of those hundreds of microservices are doing double duty. So they're not exclusively for S3. They're probably for other things as well.
Okay. All right.
But even so, it just seems like you have this service, which is composed of thousands of microservices, is just hard to reason about.
Yeah,
it's hard to imagine how they communicate and how they, how that if one of those things is broken, the whole thing's not broken. I don't know how they monitor it.
That's what I find hard to hold in my head too. And when you read about S3, you read about how it's put together, you read about the scale. It's like it's so hard to hold in your head, even at this like 1,000-foot map level. And then you zoom in and it's still like, it's just mind boggling. I guess at the outermost level, the way they describe it is there's these like API servers. Okay, that makes sense. As a client, I'm going to send HTTP requests in. I'm going to send gets and puts and deletes. There's a whole bunch of API servers that are going to handle those requests. They're not actually writing the data themselves. Then there's something they call the namespace service, right? Which has to do, I guess, with the buckets and things like, well, here's a customer and these are their containers and in object storage. They call those buckets on S3. And then eventually the data has to go and interact with an actual disk. Like it has to be written somewhere or read somewhere or deleted from somewhere. So you've got this whole other set of services which are just related to storing and retrieving data. And then you've got all these like background operations things. So they talk about how you can have replication and like tiering. So you might move from a hot storage tier to a cold storage tier to like, oh, we're virtually never going to read this. You can like put it way over out on those disks that you have in Antarctica, Amazon.
Yeah, I watched a video about the tiering stuff, and I've never really used all of the tiers, but I was kind of surprised because at the lowest tiers, the retrieval time is actually like a day or multiple days. So, I say I want this data, and I guess they probably like have a robot that goes and grabs a disk from a rack or something. I don't know.
I thought maybe they just sort of go, okay, what are like the most remote possible server data centers we have on the planet? Oh, we've got these ones in Siberia. They want us to put it in like glacier tier. So let's go dump all their data into Siberia. Those are super reliable. It's very cold there. We don't have to pay for heat for air conditioning or water cooling.
Could be on the moon too,
Yeah, they have to.
Bezos is always talking about data centers on the moon. So,
so the other thing about it is like the volume of this service, the amount of requests they get is insane. The amount of data that they're holding is insane. And S3 famously has this 11 nines of durability guarantee, right? So you put data in S3 and they have 11 nines out of the time. It's going to be 99.9 more nines. It's going to be available to you at some point in the future. In 2023, we read an interview with Andy Warfield, who's VP of Engineer, Distinguished Engineer at S3, who had a academic background in disks and storage. And he had said that S3 in 2023, they were holding 280 trillion objects and averaging over 100 million requests per second. I can't even... The mind boggles. I can't. 280 trillion objects. And then more recently, as of 2025, they store 500 trillion objects, 100 exabytes of data, and now they're up to 200 million requests per second. They peak at about 1 petabyte per second in bandwidth. I mean, they use the word planet scale for this. These numbers are just like, they don't mean anything to me. They're just too big.
In fact, they are so hard to comprehend that I had to actually look up what an exabyte is. I've heard the term, obviously, but I wasn't exactly sure what order of magnitude that was. And so I looked it up, and 1 exabyte, they claim to have hundreds of exabytes. 1 exabyte is 1,000 petabytes, or 1 million terabytes, or 1 billion gigabytes. So they have hundreds of times 1 billion gigabytes, which is, I don't know, it's a lot.
Oh, it's the mind boggles. I can't hold this information in my head. Can you imagine working on a service like this? You hope you know that when S3 has gone down, we didn't really include many examples of this, but there have been major outages related to S3 in the past 10 years, maybe 2 that I can think of. Actually, the more recent one was a DNS problem, wasn't it? Like DNS, the most recent S3, most recent major Amazon outage was a DNS thing. And yeah, that was right, because it was Dynamo. That was a Dynamo failure, not S3. But there was an S3 failure sometime in the last 10 years, and it took out massive chunks of the internet. Do you remember the one I'm talking about?
Not specifically, but I do remember there being one. And I think what we mean by that is probably the API servers became unavailable so that people couldn't get out or put in data. And yeah, we've talked about this a little bit on previous episodes, but I do worry that this has become, S3 in particular, and cloud storage and more generally, has become so prominent that it's kind of like a public utility now and is maybe too big to fail.
Yeah. I mean, it's non-trivial stuff, right? Your bank website uses it. S3 goes down. You're probably not playing Minecraft that day, my friend. You're probably not watching Netflix. These are massive, massive services that are built on top of this utility almost, right? Internet utility. It's almost like water or power for the internet. It's just weird to think about a cloud service used at such large scale that if it fails, then we're sort of just sitting there waiting for things to come back online. Probably not even working that day.
I mean, even some of the individual users of S3 are doing things at a scale it's hard to imagine. Like Splunk is a user of S3, for instance, and people are doing, bioinformatics on S3 at massive scale. And so, yeah, anyway, I guess to sum up, it's just a inconceivably large service, and it is, for all practical purposes, infinite.
Infinite is a weird word to use here. So I wanted to know a little bit about how it works. And I'm not sure how successful I was in this effort, Mike, because not only is the scale of operations so large, the number of customers I have is so large. And as you try to understand how the service works, it's like you always go back and forth between, okay, here's a aspect of the technical stack that makes up this service. And oh, yeah, they've got millions of customers and millions of disks it go firing at any time. So you also have to like go back and forth between this massive scale and this is an element of how this works. Did you come to a sense where you got a feeling of like you gained an intuition for how the overall structure of S3 works? We read a couple papers, we read some interviews, and I came away with some. How do you feel about it?
I have a better understanding than before we started researching this.
Mm-hmm.
It's still a little bit of a black box to me.
Mm-hmm.
So, for instance, as we kind of hinted at, you can put things in different tiers of storage depending on what you want the latency to be and how much speed you're willing to trade off for cost. So, like the Glacier tier that we were talking about is very cheap, but getting that data back is very slow.
Mm-hmm.
Whereas on the other end, I believe they have what they call an express tier now, which actually runs on SSDs.
Oh, I didn't know that.
I think probably the most surprising thing to me and the most fascinating thing about this is that the vast majority of data in S3 is sitting on mechanical hard drives.
That shocked me. I did not anticipate that at all.
In 2025, when this first came out in 2006, that wasn't a surprise, but the fact that that's still the case in 2025 was a little bit surprising to me.
Well, maybe one way to get into this conversation, a doorway for us to start walking through and trying to understand how it works, is the operations S3 allows on these objects are like typical CRUD operations. So you can put one, right? That's an HTTP method put, which means you're writing some file up to the disk. And you can get one back, which means you're reading it or you're reading metadata, or you can delete one. So pretty much, what does it mean for them to write an object or read an object back for a client or delete an object? And the real shocking thing is they use hard disks to do this. And it was kind of like, wait a minute, remember hard disks? Like they're mechanical spinning disks. And we read this interview, and at the time they were like, oh yeah, the biggest ones we're able to buy are 26 terabytes. It's just 26 terabytes of spinning disks. And it's crazy, but their volume is such that they have millions of disks, and the cost differential between hard drives and SSD solid state drives, even today, is it's large enough that when you get to million, I mean, even pennies, but we're talking like these are less than half the price of solid state drives, and they're running millions of them. So the cost savings is like bonkers large, vast amount of savings for them to use hard drives. But then they've got this problem, right? Because a hard disk is a mechanical thing. There's these spinning disks inside, and there's a head that reads data off the disk. And the head has to move to the right, physically in space, move back and forth to the right disk. And then the disk has to spin to the right location. And then the read head has to actually read the data or write the data. And all of this physical movement requires time. So like when you just write a file up to an object, up to S3 using the default settings, it's pretty fast. When you read one out, it's pretty fast. And as a service, it probably wouldn't be that viable to use for the whole internet if it weren't by default pretty fast. So it's insane that they're using all these hard disks with the amount of not insane, the amount of engineering effort that they put into it in order to use hard disks is what's fascinating. And obviously they're saving huge amounts of money by using an older technology, because the SSDs are so much more expensive. That surprised me. There's actually a site called diskdrives.com, and it aggregates all of the storage media prices that are available on Amazon. And I just looked at it this morning, and you can buy hard drives at about $10 per terabyte via what diskdrives.com reports. Their current price for solid state drives on Amazon is closer to $60 a terabyte. Now that's probably changing. I don't know, like the way market forces are making these prices shoot up and down, but that's insane.
Yeah, I think I had read that SSD prices are on the high side at the moment because there's
those darn AI data centers.
Yeah, the price difference is very significant. And so, and like you say, there are literally millions of these 26 terabyte drives. And so they, when you start doing the numbers, that's a lot of money to spend on drives. Plus, it's not like they are buying them once and then they're good. With this many, I didn't find any statistics, but with this many drives, I would guess that the mean time between failure is such that they probably have, a full-time crew swapping them in and out.
I would bet so too. If you said to me hard drives, HDD, that's, my immediate reaction, this is probably pretty naive, is, oh, nobody uses those anymore, right?
Yeah, I mean, if you are buying a personal computer, you can still get them. I guess it was surprising to me that this was a viable option, but when you start reading their engineering, you realize why it is and what they've done to make it viable.
Yeah. So all the movement we were saying, it takes a lot of time. There's a 2023 article on BetterStack which describes this in pretty good detail. I actually really liked, and they say there that like the mechanical movement in a disk, you can break it down into the head has to move to the right disk, the disk has to spin to the right place, and then you've got the actual data transfer. So the head moving to the disk can take up to 25 milliseconds. Spinning the disk can take up to another 8 milliseconds, and then reading and writing, usually you're talking about two milliseconds at the most. But that's potentially a huge amount of time. And so in S3, they've done a massive amount of work to engineer around mitigating the slowness of these disks. Andy Warfield, he says that if you're doing random reads and writes, random is an important term there. We'll go back to that. You could probably do about 120 operations a second. But again, S3 worldwide is doing 200 million requests a second. So that's pretty massive difference in scale. They have this really good analogy. Did you see that 747 of the blades of grass? I like that.
Yeah, it is. It's a good metaphor, and we should probably read it just so that people can get a feeling for the.
Can you read it? Yeah, I liked it too. I was like, oh, that's pretty good. And it was a good way to like picture in my head what a mechanical disk, a hard drive is doing.
The way he puts it is, imagine a hard drive head as a 747 flying over a grassy field at 75 miles per hour.
75.
The air gap.
Sorry. Okay. 747, grassy field. 747's flying at 75 miles an hour. I don't know why 7. Okay. Go ahead though. Go ahead.
The air gap between the bottom of the plane and the top of the grass is 2 sheets of paper. So, that's pretty thin.
Yeah, don't try this at home with your 747.
Now, if we measure bits on the disk as blades of grass, the track width would be 4.6 blades of grass wide, and the bit length would be 1 blade of grass. As the plane flew over the grass, it would count blades of grass and only miss 1 blade for every 25,000 times the plane circled the Earth. That's a bit error rate of 1 in 10 to the 15 requests.
So there's some details in there. It's extremely close. The distance between the plane and the top of the grass is 2 sheets of paper. What is a track width, Mike? Track width was 4.6 blades of grass wide. What is that?
So the disks are, circular,
Mm-hmm.
and
Mm-hmm.
the data is arranged on tracks that go around the circle.
Mm-hmm.
So I think what he's saying is that each individual track on the disk is 4 points would be, by this scale, 4.6 blades of grass
Okay, so
wide.
you read and write tracks. Like you're not going to read one bit probably.
These hard drives are, using the same technology that's gone been used for spinning disks for decades now, where there's tracks and sectors of tracks, and when you write a file, you're putting them on those. You're choosing a track that has an open spot and writing the data to it, and when you read it back, you have to go to that track and run the read head over that track. And so
Managing all this
um,
physical stuff in the world is so low level for my abstraction preferring brain. Can I just be out here in the nice ethereal plane of ideas? You're talking about planes flying over grass, actually interacting with physical stuff. Oh, and by the way, they make mistakes. That's another thing I didn't even think about, right? Every so often, they fail to read a bit.
one of the things that's kind of interesting here to me is that, they say it's the 747 is 2 sheets of paper above the grass, which means, a very thin margin, but also not ever touching the grass.
Mm.
So if you think about the read head on the drive, I would assume the equivalent gap on that is probably measured in microns or something,
Mm-hmm.
but not actually touching.
Mm-hmm.
So it shouldn't ever actually come into contact with the disk.
Yeah, because that's like the planes crashing, right?
Yeah.
So, okay, we've got these physical storage media, these disks, right, with these heads that are reading and writing, and they're zipping around all over the place. They're doing a lot of movement. The problem at S3 scale is I've got millions of disks. So a customer wants to send us one of their objects. I've got to write it to a disk in a durable way. And then later on, that customer is going to want to read it back out. And I've got millions of customers sending us stuff to write, to read, and also sending us requests to delete stuff. I might have millions of disk read heads all over the planet, zipping around, backing back and forth. How do I do this in a really efficient way? So the first thing that they do with writes is they just do append only, right? So you don't like write and then rewrite and then overwrite. You just always add to the most up to date, most latest spot on the disk. So you're just always appending. You want to write a file? Okay, I write the file. You want to write another file? I write a file. You want to overwrite the file you write? Okay, I write a file. And I just say this is the latest version of it. And so that write head is kind of always progressing forward. All right. All right. How'd I do there? Does that make sense?
Yeah, that makes sense. I mean, if you think about the mechanical actions that would be required to overwrite a file, you have to find the track that it lives on and the sectors in that track. And so, not having to go through that searching process definitely saves you milliseconds.
Mm-hmm. The other interesting thing is that they're using randomization to figure out where to actually write these things. That's kind of shocking to me. It's like, well, wait a minute. Aren't you going to have to read it again someday? You're just going to like randomly scatter it around these millions. And then for durability, they break each object that we send them into shards, right? So they break it into chunks,
Right.
and then they store those chunks on random servers in the fleet. And so reading then becomes like, concurrently reading all the chunks at once. So the goal with writes, you're writing one giant log. That way you don't have to move that mechanical disk head again. You don't want to write into random locations on the disk. You just write in one stream. But now you've got millions of disks to choose from. And what's the goal there, I think, is we don't want to, like, if we go, oh, this disk A in New York, it's pretty fast. Let's send everybody's writes there. That obviously won't work. So you want to kind of spread the load around. And this is one of the first theoretical ideas of this. It took me I had to really like think about what they were saying here. Did this make sense to you where they pick a disk?
Yeah. So there's two things here which I thought were fascinating and kind of surprising. One is in one of the articles, he talks about how if you're reading a big file from S3, you may actually be reading from millions of disk drives. And, he says in the article, I'm not kidding. I'm not exaggerating, really, which is surprising to me. So it's not like if you have a giant file, they're trying to write it all onto one hard drive and then reading it back off of that hard drive. And then the other thing so I had some experience with, big disks and data centers in past lives. And typically when you were trying to do relatively reliable, fast disks stuff in your own data center or like a colo, you would use these RAID drives. So I won't go into RAID too much, RAID, but there were these techniques for doing like replication of data and what they call striping. And so the idea was that, you would both make multiple copies of the data and also put it onto multiple disk, spinning disks. So you could get it faster and also be relatively certain that, you weren't losing data if one of those disks were to blow up. And they don't do that, which was, I guess, not too surprising considering, they are trying to maximize their use of these disks, but also they have this 11 nines guarantee. So they talk about the way they do replications is what they call erasure codes.
I got confused by that part, the Solomon Reed erasure coding stuff.
Yeah, it's a pretty interesting thing, and I don't think we're going to probably be able to explain how it works in here. But
I'm not even going to try, but I will let you try.
The important thing is, like you said, they divide the object up into shards, and it may be a very large number of shards. And when they read that back, they want to be able to make sure that they're, actually getting the right data, the correct, non-corrupted data with a pretty high degree of confidence.
But they don't want to duplicate every single object ultimately, right? That's what this is about?
Yeah, they don't want to actually write the data multiple times to different disks as you would with like a RAID drive. So they do this thing called erasure coding, and I think they imply they specifically use a variation of what's called Reed-Solomon encoding. The way this works, very high level without going into the math of it, is they break up the data into a bunch of pieces, and then they also compute these sort of checksum pieces, and they write those to the disk as well. And the way these codes work is that if you can get to a certain subset of those chunks, you can reconstruct the data in its entirety.
So you replicate some of the chunks. Is that right?
Well, you're writing more data than you would if you were just writing the object. So you are adding some extra storage when you're writing with these codes. But the benefit is it's not totally replicating the data. You're not making a distinct copy of it.
Full duplication, yeah.
But if some subset of the disks fails for some reason and you can't get the data, you can reconstruct it from these pieces that you've computed, which is kind of cool and mind-blowing. But it's also pretty mathy.
So those are the erasure codes. You break it up into shards. You duplicate sort of pieces of it, but not the whole thing, and you can get pretty durable. And then to actually pick a server that it lives on, they use this cool thing where they randomly pick two servers, and then they say which one has less usage. The least used of these two randomly chosen servers is the one we're going to write it to. And you're like, well, wait a minute, but you got millions of servers, millions of disks you could put it on. And so what's interesting about this, again, at their scale, is they're randomly picking two servers out of millions of times, right? 200 million requests per second. However many of those are writes, they're randomly pulling two servers out of a hat millions of times a second and always picking the least used of those two. And it ends up distributing the load really well. I find that pretty fascinating. It's like, we're just going to do millions of random selections, and then we're going to end up saturating the whole field of storage space.
Yeah, this I really love.
I
I
loved it
don't
too.
understand
I
it.
was like, well, that's
I don't.
rad. That's rad.
Yeah, so the idea is, they've got these millions of disks and they can't like monitor the load on all million of them and check it every time they want to do it right. So you might think offhand, well, I'll just choose one at random. And you'd think, that's if I choose one at random uniformly, it's probably going to work okay. But apparently it does not. And what they found is if they choose two at random and then choose the one with the lower load, that for some reason works.
Mm-hmm.
And I don't understand why, but it's an amazing consequence. I really want to sit back and think about this at some point, or have somebody explain it to me, because it's a fascinating idea.
Yeah, I mean, you could ask a kind of dumb question: why two? Why not three? Why not four? Right? Why is two the sweet spot? Obviously, it's the fewest number possible. I mean, aside from just randomly picking one. It is an interesting property of the scale of their system. So this is a lot about writes, right? They're randomly picking servers to write to. And my horrifying response when I first read that is, oh, wait a minute. It's going to take me a long time to find data if I'm just randomly spewing it all over the place, right? Like that sounds like a lot of work to make sure that I can read it easily again. And of course, they're keeping track of where it goes. I mean, that's not the problem. The problem is you don't know when and where the reads are going to happen. Again, 200 million requests a second. What if all of your customers, they all wake up and start doing business at 8 a.m. In New York on a Wednesday, right? And maybe all of their data happens to be located on the same disks. And so they're all trying to read that data at the same time. And that poor read head is struggling to spin back and forth to the location where those customers' data is located. So they call these hotspots. And they say that's like, they talk about it as heat, right? Heat management, meaning all of our customers are trying to read from the same spot. So Andy Warfield, the VP who was interviewed in 2023, he says one of the biggest and most interesting technical scale problems that I've encountered is in managing and balancing I/O demand across this large set of drives. So we refer to this as heat management, he says. And by heat, again, quoting from him, I mean the number of requests that hit a given disk at any point in time. If we do a bad job of managing heat, we end up focusing a disproportionate number of requests on a single drive, and we create hotspots because that drive has a ceiling. I'm going to paraphrasing what he's saying. There's a limited I/O that's possible. And so they have to figure out how to optimize this. And they want to place the data across the disks in a way that minimizes these hotspots. But here's the weird thing. Again, because it's a planet scale service, any one of their customers or group of their customers, their read loads are real bursty, right? They're going to wake up and read a bunch of stuff, and then they're going to be quiet for the rest of the day or rest of the period of time. And if you aggregate those bursty loads, if you have millions of requests per second and the bursts are happening all over the place, you end up with kind of a pretty uniform pattern of access. So pretty constant level of access. And this is another area where at their scale, the solution to the problem emerges because there's so much usage. I don't think I'm doing a great job describing this, but it's like you got to see this graph of if you just have a few bursty customers, then yeah, it really heats up these particular disks. But when you've got millions of customers bursting, you get a pretty uniform pace of requests. I feel like I'm doing a terrible job describing this graph that's in my head.
It's hard to describe, but yeah, he talks about how in his previous life he had worked on systems to sort of try to balance load across the storage systems, and was surprised to find that at Amazon, just because of the sheer scale of what they're doing, it tends to, and the way they've designed it, it tends to distribute itself pretty well.
Mm-hmm. So, Mike, I was trying to understand more about some of the pieces, some of the microservices involved in S3. It's like it's so hard for me to hold in my head. And I kind of have to see a little bit of this is how we built. Those are the papers I like to read, right? So I went to Amazon Science. They have a number of papers they publish every year. Publish tons of papers every year. And there were a few on S3, but the one that really stood out to me was published in 2021, and it was talking about formal methods to validate an aspect of S3, a piece of S3, one of the hundreds of microservices running it, called Shard Store. Shard Store is kind of cool to hold in your head because it keeps track of the actual written shards, right? So it's not at the layer of handling client requests. It's closer to where the storage itself is happening. That seems to me like the real meat of the product of S3. And they wrote about how they wrote a new version of this application, which they call Shard Store. They wrote it in Rust. It's about 40,000 lines of Rust as of 2021. And as you can imagine, if you have engineers shipping potentially bugs in this service, they might take down huge swaths of the internet. You don't want that. So you really want a lot of validation on top of any changes that are being deployed. And so they described this as they added lightweight. That was their adjective, lightweight formal methods. I thought this was kind of cool because it's going in a direction that I've been interested in myself for a long time. Like, how do I apply a little bit more validation, a little bit more verification without going full formal methods? And how do I do this in a way that just any developer contributing to my projects could also participate in, right? So they describe Shard Store as a key value store that's used by S3 as a storage node. So each storage node stores the shards of customer objects. This is a quote from a paper. They're replicated across multiple nodes for durability. So storage nodes don't need to replicate their stored data internally. Shard Store is API compatible, they say. So they say a production storage system combines several difficult to implement complexities. It's intricate on disk data structures. You've got concurrent accesses and mutations, and you have to maintain consistency across crashes. So that's why we end up with this 40,000 lines of Rust code. It's changing frequently. Now, internally, a shard store is a log structured merge tree, like an Elasticsearch or something like that, LSM tree, right? So in their shard store, they have a shard identifier, and these are pointers to chunks, which they store in an abstraction they call, quote unquote, an extent. I don't really like this name, but they call it an extent. Extents are contiguous regions of physical storage on a disk. So they're like, anticipating this is the storage region 100 to 1000 on this disk, and that is an extent, and it is contiguous. A typical disk they write has tens of thousands of extents. Shard Store requires that writes within each extent are sequential, tracked by a write pointer, which says, here's the next valid write position. So data can be immediately overwritten. Wait a minute, does that make sense? So data on an extent can be immediately overwritten. Okay, so they've got this write position holding write pointer. Each extent has a reset operation, and you can use that to return the pointer to the beginning of the extent and allow overwrite. So it's like, you can imagine real low-level management of contiguous sections of an actual disk. And they say that in order to keep it crash consistent, we really just append, but we append with this concept of a dependency. So this chunk is dependent on that chunk, and I will write this chunk after that chunk has been written. So you can imagine this append operation. You could build up like what they describe as like a whole dependency graph of appends. So append 2 requires append 1, which requires append 0. And you will only do append 1 after append 0. So you kind of evaluate outwards as a dependency graph. And you could sort of pass these around and evaluate them inside out. How am I doing so far? I don't think I'm doing that great of it. I'm trying to like imagine it as I'm describing it. The paper's pretty cool, by the way.
I think part of it is that you have to have a little bit of background on how disk storage works.
Why is that? Fill us in.
Well, I mean, just because when you are writing stuff to a disk under normal circumstances.
Normal. So I don't
Like
even
back
think
in,
about this crap. I just do OS write, OS read. Like I don't think about where on the disk it is.
so back in the good old days when discs were the only game in town, you'd have to think a little. You occasionally encounter things like on Microsoft, people know about the file allocation table and stuff like that.
Hmm.
So there was this thing you'd have to manage where it said, okay, here's a piece of the disk that nobody has written to yet,
Mhm.
or here's a piece of the disk that contains parts of this file. And if you want to get the whole file, you have to go to this piece and read this chunk, and then go to this piece and read that chunk. And so I think, these concepts may be less familiar to people now than they used to be, because you don't really think about tracks on disks
Yes,
anymore.
I'm in that category of people. I don't ever think about this stuff. Sometimes I do a system call, seek. that's not me thinking about the disk. That's me thinking about my file. Can I go back to usually the beginning of the file? Like I wrote the file and I want to go back to the beginning and read the thing. That's as low level as I get, Mike. That maybe is what makes this so hard for me to imagine. I did like reading this paper though, where I'm thinking about them keeping track of pointers to chunks of a disk in order to make sure that they've durably written data to the disk and that there's like dependencies between the chunks. I thought that was pretty interesting.
Yeah, I like this paper for a couple of reasons. One is because I like to see things written in Rust that are, becoming important to the world at large. But also, I think it's kind of a good endorsement of things like property-based testing, which I wish I could use more.
Mm-hmm. Yeah, so that's what I liked about it too. They were like, you know what? We're not going to write this massive formal verification spec that lives off to the side of this thing because it won't stay up to date. You'd have to have a whole team of people doing formal verification. And that's almost like if you imagine the analog of like, well, I've got a QA team and I write my code and then I try to ship it, but the QA team's in my way. The formal verification people would be like that. And they were like, we don't want that. We want lightweight formal methods. So they wrote, we found that by writing reference models in the same language as the implementation, we make them easier for the engineers to keep them up to date. And they don't have this cognitive burden of learning a new language and mapping concepts between this model and the implementations. They talk about these reference models. They talk about refining what the code does. So let's say, for example, they've got an LSM tree. And they're like, well, we're not going to mock that out. What we'll do is we'll write this formal verification, sort of like an integration test. And instead of a full LSM tree, we'll just use a hash map. Okay. But then the question becomes, how do you know the hash map actually has the same behaviors as the LSM tree? That's a different data structure. And they're like, well, we will use property-based testing. We use property-based testing to make sure that our reference model actually has the same properties as the thing that we're modeling. And then we're in business. And because it's written in the exact same language as the implementation, the engineers can fluidly go back and forth between these. And they don't have to learn a new language. They don't have to learn new concepts. It's just a model version of what they're actually changing. And I thought that was pretty cool, actually. They're like, yeah, we're not going to use these languages like Alloy and P and those other ones. We're just going to write it in Rust. And the engineers who work on this project are going to be able to contribute to it too. It felt like very viable and practical use of these tools.
And I think it's interesting to note that this is one service in the hundreds of microservices, albeit a very crucially important one. And it's also not the original storage service used by S3. It is a replacement for something else.
Yeah.
But
it's a success for the Rewrite It in Rust evangelism task force.
Exactly. Yeah.
Why did you want to talk about S3, Mike?
I think there's a couple of reasons. One is that it's so ubiquitous now. I mean, S3 is sort of like the brand name of cloud storage services. So even we haven't done a lot of research into the other ones, but my assumption is they all work in relatively similar ways.
Mm-hmm.
S3 is obviously the biggest and oldest of these, but I think people, like when we started using it back in the day, we understood why we were using it. But I think now it's become such a such a common thing that people have maybe lost track of why you use S3 as opposed to, just spinning up a disk drive or, what Amazon calls an EBS volume.
Mm-hmm.
And so anyway, I just kind of wanted to talk about like why people use these and what the benefits are and what people are using them for, as opposed like.
Oh, I mean, I'll tell you,
people are not
for myself as a customer, it's cheap, it's fast, and if I put stuff in there, and I mean, I use Azure a lot at work, so it's similar, but there's a pretty good durability guarantee. It's cheap, it's fast. If I put stuff in there, it's very unlikely I'm going to lose that stuff. And in fact, it's so cheap and so fast and so durable. I put crap loads of stuff in there that I'm never going to read.
Yeah, I think that's kind of how people started out with it. I mean, when I first started using this, it wasn't because we were putting our mission critical data in it. It was, we downloaded this. We're downloading these hundreds of files every day. We might possibly want to refer to them again, so let's keep them. But we can't really afford to put them on a hard drive. So
or in a database.
We'll stick them in S3.
Yeah, right.
Yeah, or in a database.
Yeah.
And so it was just kind of a place to park things that you maybe were going to refer to.
It's like the planet's information junk drawer.
Yeah. And I think that's probably still a common use of it. I think also, people do use it for things like database backups. So, if you want to back up your Postgres instance or something, you may not actually ever need to restore from that backup, but you don't want to store the backup on expensive disk. And you probably don't want to retain that backup for the rest of time. So you can put it in S3 and say, give it a 3-month expiry policy or something like that. And you feel fairly confident that the backup's going to be there if you need it, but it's going to go away at some point and stop taking up space.
I think the word confidence, that's the surprising feat that they've achieved here. It's like you could set it and forget it. It's not going anywhere. I mean, if you imagine that instead of 11 nines, they were like, yeah, it's pretty durable. You might lose this stuff. That's a totally different product, and it's going to be used in totally different ways. And there's no way that that's going to become foundational to huge swaths of how websites on the internet work, how internet companies are building their products. It's like that durability guaranteed and the cost. It's insane.
Yeah, so I think that's a lot of the appeal, but this kind of funny thing happened in the last 15 years, which is that large volumes of data started to become very important to the operation of companies. And there were these, many tools built to work on large volumes of data, things like Hadoop and Spark. And
wait, let's just pause with Hadoop for a second there. Sorry, I jumped in, but Hadoop's interesting because it's kind of like, normally when you write to a database like a PostgreSQL, you say, PostgreSQL, please store this. And it's got its own internal logic, right, for storing the stuff. But with Hadoop, you could actually write files, HDFS, where you want to. Am I right? That's right? And then Hadoop is a thing that can read them. So you could be like, I want to put these HDFS files all over the place. I don't necessarily want to ask. I mean, you could ask it, but in general, you could just write large volumes of data and then later query it using a thing like Hadoop.
Eventual end of this has been that people really use these systems as analytical database systems now. So, probably 10 years ago, there was this idea of the data lake that started to become prominent, and tools like Presto, which is what Amazon's Athena is based on, and which later evolved into Trino.
We use Trino at my job, yeah.
These things were built to do queries over these data files, which are often sitting in something like S3. And
these are now so-called diskless, quote, diskless databases, which having sat on the infra side, I freaking love that idea.
Yeah, and then the nice thing about those tools is you could do queries over data in sort of its original form. So it might be CSV files or JSON files or whatever, and you could use something like Presto to do a query on it using what they call schema on read idea.
I mean, how data lake junk drawer is that? I don't even know what this. I just stuff it all in S3, and then I might want to query it someday. Can you figure out what the schema is when I want to query it? And yeah, somebody made a tool to do that. I mean, that's a pretty kooky idea. I love it. A+, gold star, no notes. Can we do that?
It is an excellent idea. And it's evolved now to the point where, most people are building data warehouses in object stores like this. And there's the concept of the lake house, which is kind of a data lake plus data warehouse.
The metaphorical names just get better and better.
There's a couple of what they call open table formats now that are built on top of, they're built on top of things like Parquet files or ORC files, but in a lot of cases, probably the vast majority of cases, those Parquet files are sitting in something like S3.
Yeah.
And so you've got Delta Lake tables and Iceberg tables.
We're using Iceberg at work, and I just love that. Like, you mean I could just write crap into object stores, and then you can figure out how to query? Like, that sounds awesome. I don't need a client. Like, I'm just writing. All you want me to do is write these files, and I'm good at that. Okay, my friend. I've been doing that for 15 years. What do you? I'll write your files. I'll write my file. I'll write whoever's files. I'm pretty good at it.
It's a nice idea. It's not quite to the point where people can use them as for online transaction processing.
Right. It's analytics. It's like you've got nerds who want to aggregate how many sales did we do last month. It's not like, oh, how many units of this item do I have in my warehouse right now so that you can order it? That's not what we're talking about.
Yeah, but you can do, like with Iceberg tables and Delta Lake tables now, you can do ACID transactions on these tables, which are really defined in terms of files sitting in S3.
That's pretty weird to imagine, too. Like, okay, I don't want to try to we're already over an hour here, just in this under the spell of this planet scale service. And now we're talking about ACID transactions on top of it. Like, the layers of abstraction are kind of blowing my mind a little bit. I'm still just fascinated by the fact that I could just write crap into object stores, and you could turn that into a quote unquote database. Cool. Just let's do that. That sounds awesome.
The uses of these things have expanded beyond the I need a place to park some data that I may reference someday.
Yeah.
It's actually involved in mission critical stuff and day-to-day usage of this data for analytics and even sometimes customer-facing applications.
It's like, Mike, if you said, hey, I want to take all the junk drawers and all the houses in my city and build a database out of them. All right, well, that's been a pretty good tour of S3. Hopefully we didn't mangle some of the ideas in there too badly. We're going to include some links to some papers, a couple of articles and interviews. There's a reInvent talk from 2021, which is a deep dive on S3. The stuff is amazing. And trying to hold it in your head, friends, not easy. Just the scale of it and the amount of engineering effort that's gone into making this all work on top of very slow mechanical drives, it's mind-boggling. So hopefully you've enjoyed this tour of S3 with us. Mike, thanks so much for bringing up this topic. I want to keep reading about it, actually.
Same.
Well, this has been Picture Me Coding with Eric Aker and Mike Mull. Thanks so much. Happy New Year to all of you listeners, and we'll see you again in a couple weeks.
See you next time.
Bye-bye.